Hello, welcome to this video. So in this video we're having a look at calculating curvature of space-time in the context of general relativity. This is going to be the last video on the section on curvature, and so by the end of it we'll see a critical tensor that encapsulates everything about the space-time curvature which appears in Einstein's field equations, the kind of central equations of general relativity. Einstein's field equations to general relativity are like Maxwell's equations to the discussions of, light and electromagnetic radiation. So, the tensor we're going to be building to in this video is indispensable. And it's been, a fair few videos to get to this point because we've had to build up a very careful understanding of how we describe curvature mathematically. We talked about connection coefficients, we talked about Christoffel symbols, and in the last video we talked about geodesics. And we're going to be bringing at least the idea of parallel transport and Christoffel symbols together in this video to discuss curvature. And then in the next few videos we'll move on to talking about relativistic matter and then bringing it together to look at how matter can bend space-time. So if we're going to be talking about curvature, we need to recall what kind of thing is useful for describing curvature, principally. So remember that although in flat space in Cartesian coordinates you can use the connection coefficients or your Christoffel symbols if we express them in terms of the derivatives of our metric. That doesn't work generally because the nice rule for whether a space is flat or not for covariant for Christoffel symbols depends upon the coordinate system we use to describe that space. For example, spherical polar coordinates, the basis vectors change, so the Christoffel symbols are not zero in a flat space. And whilst in Cartesian coordinates there's a nice measure of whether the space is curved or not in terms of the Christoffel symbols, that doesn't work if we're considering that doesn't work if we're considering different representations of our Christoffel symbols, so representing them in different coordinate systems, and that relates to our Christoffel symbols not being good tensors. However, the covariant derivative is a tensor and therefore has coordinate independent meaning, and the covariant derivatives will be able to describe curvature. We've seen that they can do that through parallel transport, but if we're interested in kind of calculating an average curvature, we want kind of curvature over the manifold, so we want a kind of a tensor, ideally a rank 2 tensor involving curvature, and we're going to be working towards that. This kind of rank 2 tensor is called the Ricci tensor, but to get there we need to use the Riemann curvature tensor, which is all about the covariant derivative, and the fact that the covariant derivative as a form of a directional derivative depends upon the path taken, and by looking at how it depends on the path taken, you can infer something about the curvature of your space, and therefore go, for example, the walls of a cylinder have no intrinsic curvature, whilst our other two shapes in our colourful rainbow images do have intrinsic curvature. So if we look at the kind of Riemann curvature tensor, the Riemann curvature tensor is really about how the covariant derivative depends upon the path taken. So it's looking at, if we have a vector and and we move it across our manifold, how does the direction we are moving our vector in affect the final vector we end up with? So we can consider two directions, E nu and E mu, and the covariant derivative along these different directions will be kind of, well, different. And that means, as well, if we consider our overall path generated by moving our vector along, the direction of in nu, and then moving our vector along the direction in mu, the direction we picked first is important when calculating how our vector will change along the path. So if we have an overall path and split it up into two paths, it matters in which order the vector takes those individual paths. And we can summarise that dependency in terms of the commutator between a covariant derivative along one direction and another, so along our kind of subpaths. And we might wonder, okay, our curvature is ultimately going to relate to the commutator of covariant derivatives. But is our expression then going to be something as simple as the commutator of two covariant derivatives multiplied by the component of a vector, or really acting on the components of a vector, equals some curvature tensor multiplied by the components of the vector? But that's not quite true, because if we are parallel transporting our vector, then, along one of the paths, or maybe both of them, so maybe, of course, both in nu and in mu, then, we're going to end up with the commutator of 0. However, a commutator of 0 doesn't mean that our object doesn't have curvature. It just means the path we picked happened to parallel transport our vector, or correspond to geodesics across the manifold. And therefore, we need a situation where our commutator between our covariant derivatives is 0, but the curvature isn't 0. So we have to have the commutator acting on the components of the vector. The commutator of the covariant derivatives acting on the components of the vector is equal to some curvature tensor multiplied by the components of the vector minus some other term involving components of a vector. And that minus other term will allow the curvature to be non-zero even when the commutator between the covariant derivatives is 0, in the case where we've picked parallel transported paths. And actually that condition, that this other term with a minus in front of it has to cancel out the curvature in the cases where we're parallel transporting our vectors, that condition actually tells you what form this other term is going to have to take. This other term is a connection coefficient multiplied by the covariant derivative of the components of the vector. This covariant derivative, you'll notice, is kind of a covariant derivative along a different direction. So it's not necessarily going to give 0 even when the covariant derivative along mu or nu would correspond to 0. Now this is our form of our description of curvature, and the part that really tells us about the curvature bearing in mind that the commutators isn't quite, because we could have the commutator being 0 even when we do have curvature of our manifold. So the part that tells us about the curvature itself is this rank 4 tensor with the symbol capital R. And R has one index on the top and 3 indices on the bottom. And now we're going to break down to really kind of like explore what this R represents. And then we're going to look at contracting it to get the Ricci tensor and then the Ricci scalar, and it's the Ricci tensor and the Ricci scalar which will appear in our Einstein field equations. Now it's worth saying when interpreting the Riemann curvature tensor, in terms of a purely mathematical perspective, beyond what we have already mentioned, there is a way to do it which is fairly intuitive, which partly explains why the Riemann curvature tensor is a rank 4 tensor, despite manifold being described by a rank 2 metric. However, that description isn't too useful to us, really, because it's one of those where, curvature is to an extent arbitrary in that what we describe to be curvature or not. And it's also very complicated. And a mix of those two things means sometimes it's not actually worth going into certain ways to explain things, and it's worth just mentioning it to leave it for listeners to explore if they will. But I think it is helpful breaking down the Riemann curvature tensor a little bit. Even if when one breaks it down, it becomes slightly like, is that the only way to think about curvature? And it's like, there are probably other ways. But anyway, if we want to break down the Riemann curvature tensor, we rearrange the equation we had before to make our Riemann curvature tensor the subject of our equation. Then what we do is we replace our covariant derivatives with partial derivatives and crystal symbols, and we make use of symmetries of products of partial derivatives and also symmetries of crystal symbols, and then we end up with this equation for the Riemann curvature tensor. I'm not going through the derivation from the top to the bottom line because it is literally just inserting things into the top line and then using symmetries, which we have talked about in depth in this playlist. But once we've got our bottom line, we can see that really the Riemann curvature tensor has 4 terms in it. 2 pairs of terms, with each pair having a fairly unique meaning. So if we look at the first pair of terms, we can see it's the partial derivative of our crystal symbols, but importantly, it's a partial derivative of the crystal symbols in a different but allowing for the fact that this partial derivative could be in a different, in a different spatial direction to the change in the basis vectors that the crystal symbols are describing, because we have a different index for a partial derivative than we do in our crystal symbol that is next to. And so a way to interpret this kind of pair of terms is that it's telling us how the metric is changing in different directions. It's something similar to something you might see in further maths, where one could be looking at potentially saddle points. And saddle points is really looking at where, a curve changes, but you're looking at the components of that change in a different direction. So this part of the Riemann curvature tensor is really, if you like, about almost like, well, yeah, it's kind of like, it's how the manifold is shifting direction. It's sort of what's going on there. Well, yeah, already about how the curvature of the manifold is shifting direction. That's probably a better way to think about it. Our latitude terms in our Riemann curvature tensor are products of critical symbols. Now, the products really here are therefore going to be combining, well, in each product we're going to have a combination of two covariant derivatives. And so this is looking at how the covariant derivative is changing by comparing two covariant derivatives. And we can see that if we substitute our expression for the critical symbol into the critical symbols, and we end up with this rather long equation. But, you know, this is essentially relating to how the covariant derivative is changing, but importantly, how it is changing in terms of, well, some kind of rearrangement of your terms, because we can see that what we've done in our term in our brackets is we've flipped the nu and the mu, and we've kept other things the same. So we're kind of comparing what it's like transporting along one direction to another in terms of our covariant derivatives. And so, yeah, we're essentially looking at something involving, multiplying the change in one direction by the change in the other, and then subtracting that from that situation reversed. And, this is essentially about how the connection coefficients have some kind of measure of direction encoded into them, building on from the idea that our critical symbols don't necessarily commute. And it's that lack of commutativity which is giving us this kind of the importance of this expression. So really that's kind of a summary of the different parts of the Riemann curvature tensor. In parts that's not too solid. The reason being is that there's many ways to think about curvature. So when one is getting to the details, there are ways to get around it, but to give a whole coherent picture for the tensor, if we just split it apart, the picture becomes somewhat less solidified. Well, what we're now going to do is look at contracting our Riemann tensor to get a tensor with, with two indices, and therefore get a rank 2 tensor, which is very compatible with the metric, which will allow us to then get to our Ricci scalar, which describes the overall curvature of our manifold. And we talk now about the Ricci, the Riemann curvature tensor, but there's a lot of kind of indices present in the Riemann curvature tensor. I mean, in space-time, which is four-dimensional. Each index can range from 1 to 4. And so there's a lot of different ways to arrange the indices present in our Riemann curvature tensor. So we want some way to really reduce the number of terms, if at all possible. And we want to get from the Riemann curvature tensor, because this is the tensor that is actually describing the curvature in many, many directions. So what you can do is you can look at our expression for the Riemann curvature tensor and think, well, what would be a nice size of tensor to deal with? Well, our metric is actually essentially our metric has two indices. It's a rank 2 tensor, so it'd be nice to get some kind of rank 2 tensor from our rank 4 Riemann curvature tensor. And this rank 2 tensor turns out to be the Ricci tensor, which I think is kind of quite a cool name. And we get it by essentially contracting one of our indices, well, or one indice on the top and one of our indices on the bottom. Now, due to certain symmetries of the Riemann curvature tensor, you might see this written slightly differently. But we need one on the top, and there are rules regarding where it must be on the bottom. Now, we can use Einstein's summation convention and just recall that we cancel out repeated indices above and below, meaning in terms of if we're using the tensor in this form in kind of calculations, this tensor actually acts like a rank 2 tensor, and we call this rank 2 tensor the Ricci tensor, which, because we've contracted the top index and the middle index, we're left with just our indices sigma and nu, and these are our indices of our Ricci tensor. And to understand what the Ricci tensor really is, we can replace our crystal symbols with our definitions, so with our kind of covariant derivative in this case, and then you can look at, okay, if we're looking at a situation where we're parallel transporting, essentially, along a vector u, and we're indexing the components of u as u lambda, and the basis vectors of u as e lambda, then essentially, the kind of covariant derivative of u lambda is going to be 0, and that will leave us with essentially this kind of Ricci tensor describing the product of our crystal symbol and our covariant derivative. But if we replace the crystal symbol with our definition, we can see that the essentially Ricci tensor is going, well, if we parallel transport a vector along a particular path, then how would the components of the vector and the basis vectors associated with this path, how would those things change if we were going to take it along a non-parallel transported path? So it's kind of looking at how parallel transported things wouldn't remain parallel transported if we picked a different path. That's the bulk of it. And it's given by essentially the product of the change in the basis vectors along, well, that governs the parallel transport path along a different path, and the change in the components of a vector, you know, across the parallel, well, which were across the parallel transported path when we shift it to a non-parallel transported path. So it's, going from parallel transported to perhaps not parallel transported. That's a way to think about the Ricci tensor. It's essentially deviation from parallel transport. And, in kind of general relativity, we won't be using the four-Riemann curvature tensor because it just has so much information. We don't need all of that information. It will turn out that the Ricci tensor is actually perfectly sufficient for what we want to do. Really, the Ricci tensor is, generally speaking, just as good as the Riemann curvature tensor. The Riemann curvature tensor has a more, it has a richer description of curvature, but we don't need that degree of richness. We don't need to break down curvature in so many ways. So the Ricci tensor is all well and good for our purposes, but we can go one step further and get the Ricci scalar, which is a zero rank tensor, and then we can combine the Ricci tensor and the Ricci scalar to get our Einstein tensor, which appears in our Einstein field equations of general relativity. So we'll be using the Einstein tensor a fair bit. So the main real idea behind the Ricci scalar is that when we were looking at the, the Ricci tensor, we had some description of curvature, but it was more elaborate than what we actually need. In some cases, even the Ricci tensor. Let alone the Riemann curvature tensor. And that's because the Ricci tensor is talking about curvature, for of different kind of dimensions within space-time. It's not looking at the overall effect of curvature. Now, we'll need the Ricci tensor to get our metric, if we know how matter is distributed. But if we're just interested in general curvature, and so we're going whether, globally is the space flat, or is it not flat, or how much is it curved, the Ricci tensor contains too much information. Well, not too much, it just contains more than we need. Whereas the Ricci scalar will describe the average curvature across our manifold. And when we're doing averages, we can recall that, averages is given by a trace over a matrix, if you like, particularly if the matrix is a diagonal matrix. And, because it's a thing because the Ricci tensor comes from the Riemann curvature tensor, and the Riemann curvature tensor comes from covariant derivatives and Christoffel symbols, but both covariant derivatives and Christoffel symbols ultimately come from the metric. Because all of that, ultimately the Ricci tensor is symmetrical. Also, if we express it as a matrix, it would be a diagonal matrix, due to the fact that we're working with symmetric metrics. And so the average, if you like, the weighted kind of average, if you like, of the Ricci tensor is the Ricci scalar. Now you might go, if we can find an average, don't we have to divide by the total number of terms across our diagonal matrix? But because kind of we're not really changing the the size of our matrix that we're using to represent either the Ricci tensor or our metric. There's no real point rescaling by dividing by a set number, because that number will be the same in all cases, because in all our spacetimes there will be the same number of diagonal terms describing our Ricci tensor, and similarly describing our metric. If you were working with a situation where you were considering, maybe some strange manifold where the number of dimensions of the manifolds shift, then you might have to worry about, dividing by the number of terms along the diagonal, because that might fluctuate. But for our purposes, the number of terms along the diagonal is a constant, and therefore, it has no real physical meaning because there's nothing to measure it against. So we take the average of the Ricci tensor to, just be essentially the sum of terms along the diagonal of the Ricci tensor. But we have to take account that space-time has some kind of Lorentzian-like geometry, or general relativity is pseudo-Riemannian geometry, and therefore, we're doing something essentially to the equivalent in the Euclidean space of adding up all our terms on the diagonal. It's not quite like that, because, we have a non-Euclidean metric, and importantly a metric where if our time term is negative, the space terms are positive and vice versa. So it's a lot more complex, but it's the same root idea. We get an average by taking the trace of a matrix, and we take the trace by multiplying our matrix with the inverse metric. So as I say, the Ricci scalar R is describing some kind of overall curvature of our manifold. And to look at a few examples, we've got some images here. So a sphere, for example, has positive curvature. So the Ricci scalar is a positive number. Now, positive essentially means that if you go away from the equator and you start with two lines that are parallel, they're going to converge. They're going to meet at the poles. So, spherical geometry has positive curvature because it's due to parallel lines converging as you parallel transport them across the manifold. Whereas for, other shapes, if you move the lines away from the kind of, if you like, equator, or like the middle of the shape, the lines diverge. So parallel transport into parallel vectors initially corresponds to the vectors diverging. And, here the Ricci scalar would be a negative number. And going back to what I said before about a cylinder having no intrinsic curvature, if you were to calculate the Ricci scalar for the vertical walls of a cylinder, you would get that the Ricci scalar would be 0. The same as for flat space, because a cylinder on its vertical walls has no curvature, so the average curvature is 0. So the Ricci scalar is really good for allowing us to see at a glance what kind of global or overall geometry our manifold has. In terms of getting a metric from a distribution in matter, it's not nearly as useful. But if you see a space and you're giving the Ricci scalar, you can immediately get a sense for what that space may look like. And another thing to mention is the amount, or the rapidity, speed if you like, at which parallel transport results in lines converging or diverging, is given by the size, the magnitude of the Ricci scalar. So, if we had a sphere, and we made that sphere really, really small, because it has a small radius, lines would very, very quickly converge if they went from the equator to the poles, and therefore the Ricci scalar would be quite big. So in short, the Ricci scalar gets larger for a sphere as the radius of the sphere gets smaller. And that's why, kind of like at the heart of a black hole, we have a problem, because, if we ignore quantum mechanics, we appear to have some kind of singularity. And singularity, or our manifold is compactified to a point. And if we're looking at non-rotating black hole, we started off with a spherical geometry, so the curvature at the singularity is going to be given by taking our sphere and squishing it to a point with zero radius. But because the curvature gets bigger as the radius gets smaller, our Ricci scalar, or the curvature at that point, becomes infinite, and that is a problem. General relativity can't really handle that, but it can handle finite values for our Ricci scalar. So we've gone on quite a long journey. We've gone from a Riemann curvature tensor to a Ricci tensor to a Ricci scalar, and now we're going to bring our Ricci tensor and our Ricci scalar together to describe our Einstein tensor, which appears in the Einstein field equations. So we talked about a couple of tensors so far. We talked about the Ricci tensor. We talked about the Ricci scalar, which is technically a zero-rank tensor, and now we're ready to bring them together into the Einstein tensor. And the Einstein tensor captures everything about the curvature of space-time. And in the oncoming videos, we're going to look at how matter impacts the curvature of space-time. And therefore our equation for kind of general relativity will look something like Einstein's tensor equals some other tensor involving the distribution of energy and matter in space-time. And those of you who have looked at special relativity might be able to guess what full vector might be the basis for a rank 2 tensor describing the distribution of energy and matter around space-time. It's something to think about in terms of thinking about where we might be heading, because it's always good to use your knowledge of special relativity to look at things in general relativity, because the two are very, very connected. But anyway, on one hand side of Einstein's field equations, we will have the Einstein tensor describing the curvature of space-time. And the Einstein tensor has a capital letter G. I'm not sure if this was intentional, but it's the same letter we use for Newton's constant of gravity, and it's kind of fitting, because it's this equation that encodes gravity into space-time. Everything about gravity can be seen in the Einstein tensor. Now, obviously, if our space-time is flat, if our space-time is flat, all components of the Ricci tensor are zero, the Ricci scalar is zero, and therefore the Einstein tensor is zero. If our space is curved, then we're having non-zero components, at least some non-zero components, within our Einstein tensor. And another way to think about the Einstein tensor, although this is a lot more of a fuzzy way to think about it, but you can kind of think about the Einstein tensor as the difference between a tensor that is describing kind of curvature at particular points, if you like, in space-time. It's not particular points, for particular combinations of dimensions, which we encapsulate within our Ricci tensor, and then some kind of average curvature of our manifold. So each component of our Einstein tensor will be kind of the difference between the curvature at that particular point in space-time and some kind of average curvature over space-time. And that kind of makes sense because, if space-time is like evenly curved, well, has the same curvature everywhere, in what way is that, that shouldn't, well, that wouldn't really refer to, it's hard to say clearly, but that would refer to some kind of uniformity. Whereas the interesting thing about how matter is distributed is the way you have non-uniform distribution. So you want non-uniform curvature. As I say, it's a very fuzzy way to think about it. We might be able to be a bit more specific in particular cases. And due to the symmetry of our Ricci tensor and the metric, we can say, well, due to the symmetry and the fact that the metric is, well, our connection coefficients are metric compatible, we can say that the covariant derivative of the Einstein tensor is 0. And from that, since our connection coefficients are metric compatible, you'll be able to deduce that, this Einstein tensor having 0 as a covariant derivative must imply that the covariant derivative of the Ricci tensor is also 0. So you could start from the bottom statement and then work upwards to work out properties of the Ricci tensor. But if you were to derive the bottom equation, you would use properties of a Ricci tensor, and then that would imply that the covariant derivative of the Einstein tensor is 0. Now, in this video, there's been a fair bit of, lots of technical terms, lots of different ways to think about things, and isn't too specific. And that's because it's very hard to get a handle on the specific nature of our mathematical objects when independently their meaning is somewhat flexible. What matters in physics, though, is how concepts connect, and it's those connections, and not the definitions of connections we've been using in differential geometry for this playlist, but the connections between our different terms that really cement what these things actually are. So, the Einstein field equations, which we'll come on to after looking at how energy and matter is distributed and how that kind of impacts space-time, the kind of Einstein field equations look something like this. At the top, we can see in the kind of pink. So we have the Einstein tensor, and then we have an additional term before our equal sign, and this additional term is corresponding to the presence of dark energy. And because dark energy seems to be causing a accelerated expansion, which doesn't really distinguish particularly between the dimensions of space-time, we get the term corresponding to the change in space-time due to dark energy by having a term which is some scalar multiple times our metric. Because dark energy doesn't specifically affect one dimension of space-time, it kind of affects them all kind of in the same way. So we can characterise the dark energy by either a tensor of a scalar multiplied by the metric, or if you like, just the constant itself, and the constant is this capital lambda, which looks like a kind of triangle with base missing, and we call this the cosmological constant. Whether it is constant is open to debate. And then on the right hand side of our equation, which will be what the next few videos will be concerned with, we have a term involving the Newton's constant for gravity, and this has to enter into Einstein's field equations because under appropriately weak curvature, Einstein's field equation should reduce to Newton's laws, so we need that capital G present. We've got a few other constants, and then we've got a rank 2 tensor describing how energy and matter is distributed. And as I say, I'll leave it to your imaginations for now to guess what 4-vector we might build this rank 2 tensor from. But that's everything for this video. I know in parts in this video the explanations have been mildly kind of woolly at parts because it's kind of arbitrary to an extent how we describe curvature. As I say, what matters is how everything ties together. So how curvature ties together with the presence of matter in space-time, and we'll be looking at the presence of matter in space-time in the next video. But it's been brilliant having you here on this, been brilliant kind of sharing all this wonderful physics with you, and hope to share some more wonderful physics soon. But until then, stay curious, enjoy exploring the maths, and I look forward to seeing you at a later point in the manifold of space-time.